By and large, the breakthroughs in quantum technology are of a character that's similar to all of the other technological developments that have come before. I don't personally think there is anything truly different about the development of quantum technology. But for instance, some of the things that have been motivational in our community relate directly to security. Quantum computing, the development of computational technologies that are able to crack public key encryption systems are obviously of great interest for security agencies, for governments, for private organizations worldwide. But more generally, I think the advent of technologies that are powered by exotic quantum effects, as we've talked about in the last couple hours, really show that there's a whole host of new capabilities that range from applications in mining and standoff detection for military purposes through to more or less the way we organize society. And that comes from these really ambitious goals that our community is developing associated with the production of so-called quantum simulators, things that are able to solve major problems in materials science and in chemistry that, while they sound esoteric, are actually directly linked to the way we generate and disseminate energy globally. And that, of course, has massive impact on the way we organize society, we organize cities, and as we heard in some of the discussion today, has major ethical and political as well as security questions about how we support a large and growing human population. I mean, quantum mechanics has had an enormous impact on everything around us. We speak somehow about the quantum revolution as if it has not already started to occur. The fact is, almost everything around us is powered by our mastery of the most basic phenomena in quantum mechanics. If you own an iPhone, for instance, you'll have many semiconductor power amplifiers as well as a microprocessor or more, chipsets associated with microwave and radio frequency communications. All of these are powered by our understanding of quantum mechanics. And what ends up happening when you tally all those things up, when you tally up all the light-emitting diodes, all the laser diodes that exist in kind of the technology you carry around with you, you find that in a typical room with a few dozen people, you rapidly get to counts of tens of thousands or even hundreds of thousands of individual items powered by quantum mechanics. Obviously, that's going to change depending on exactly the way you count. If you count each LED in an OLED display, it'll be a little bit different. But this ubiquity of quantum mechanics is kind of underappreciated. That it's also pervasive not just in our kind of modern information technology, but also in the way we do medical imaging, the way we do communications. The fact that we drive around with GPS systems in our cars that are powered by atomic timekeeping devices. Right? These are really remarkable things that I think are insufficiently appreciated by the general population. The first quantum revolution was about harnessing the basic properties of quantum mechanics associated with large ensembles of quantum systems. So for instance, if you have a solid material that contains many, many electrons, the electrons being the negatively charged components of atoms, in the large ensemble limit, quantum mechanics tells us how those electrons will behave. For instance, this tells us how certain materials will become metallic, that is, they conduct electricity, or they'll become semiconductors. They can be switched on and off in terms of their ability to conduct electricity. That, of course, is what powers microprocessors. Transistors work because of these bulk effects. But completely separate from that is a new kind of reckoning in technology and technological development associated with harnessing not just what happens when you put all these things together and you look at the average over all these properties, over all these particles, but rather what happens when you access individual quantum systems, individual systems that obey the laws of quantum mechanics, and then you harness and control the most exotic phenomena that for a long time were kind of brushed under the rug as mathematical oddities. The things that we hear about as superposition, the idea that quantum mechanical systems can be in more than one place or more than one state at once, or entanglement, you can have these inextricable totally non-classical links between particles that are separated by enormous distances. Our hope is to use those things as resources to power technology in a way that's very similar to the development of technologies powered by the flow of electricity. That idea of exploiting quantum physics as a resource is what underpins this second quantum revolution. There are quantum mechanical analogs of current. There's something called probability current that you learn about in first year quantum mechanics. I use this idea of the flow of something to provide powering of a technology in a way that's a little bit more abstract than the literal interpretation. I spoke about the way we use the flow of water to drive, for instance, a water wheel powering a grist mill or something as such. Then the motion of steam, where we have some mechanical actuation leading to the generation of, say, motion. Separately, we learned about the flow of electricity, giving us the ability to power technologies like computers or telephones or anything like that. It's not 100% obvious that we'll be harnessing these exotic quantum effects in terms of the flow of energy or matter in order to provide new capabilities in technology, but rather the idea that we're harnessing a kind of source of power. And I use that term power in the kind of loosest vernacular sense, not the physics sense, in order to give rise to new technological capabilities. The development of quantum computers that are capable of hopefully one day cracking public key encryption systems is highly motivational to a wide variety of parties, from government agencies and private organizations to individuals like myself who are interested in kind of seeing what we can do. My personal view is that over the last several years, even though we've seen tremendous growth in our capabilities to access and control quantum systems in a way that might in the future be useful, it seems like our understanding of what exactly would be required to build a full-scale quantum computer capable of beating any classical system in this one specific problem of factoring is so large that I am personally not motivated to dedicate my career exclusively to that. Instead, it's become really exciting to think about what we could do with much smaller systems, where the kind of power and the scaling of phenomena in quantum physics can still give immense computational or other technological benefits that are a little bit distinct from this challenge of encryption or decryption. Instead, my group is focused on trying to learn how you can control quantum systems towards some useful end, whatever that end might be. And it's derived from an engineering discipline called control engineering, which impacts everything around us. It's what makes airplanes fly. It's what makes computer memory work. The same idea is what motivates me, the idea of grabbing control over quantum mechanical systems and then helping others who wish to apply them in a useful way. If a Stuxnet got into my control system, pretty much nothing, right? We have small experimental systems with small numbers of atoms. We can control them, we can perform some manipulations, and really what we're trying to do is measure these quantum mechanical systems. Ultimately, the system would just break, and we would probably have to rebuild one. More generally, I think the nature of your question relates to if you can develop these kinds of technologies and then they become exploited by some third party with malicious intent, what would happen? I think that's an interesting question that we just don't know very much about, because it's not like there's some convention about the way we program quantum technology. The reason Stuxnet or similar malicious software can wreak such havoc is that we have kind of widely accepted protocols and standards for the way we operate computers. We have Windows or we have OS X. These things are common enough that people can develop malicious software that can infect them and put them to some nefarious use. We haven't reached any kind of development in quantum technologies that's similar to that. If we do, things might be quite different. Decoherence is a major problem for us. My group in particular is focused on trying to develop control techniques that prevent decoherence, right? It's a major problem in our community. It is motivational for us to ask the question, why it is that quantum mechanical things cease being quantum mechanical, and can we overcome that? There are lots of historical precedents that indicate our ability to exert control over technologies can overcome some similar problems. The best example that I really enjoy is DRAM. It's a kind of memory that powers your computer. And DRAM itself is not stable. It doesn't hold memory states. And what we do is we apply control in the form of what's called a voltage strobe or refresh to kind of recharge all the cells in your memory. And you don't experience a piece of hardware that decays over time. You experience one that to you is able to store memory. And yet it's only functional because of access to these control techniques. It's interesting to people like myself and my colleagues who have been funded by agencies like the Army Research Office and the National Security Agency for many years in a completely open, university-based, publication-based, knowledge dissemination-based way, to have seen articles in major media outlets that spoke about the NSA's investment in quantum information in some kind of nefarious or underhanded way. So, people think all sorts of scary things are going on behind the fence, and that agencies like the NSA, which have developed a kind of unsavory reputation, their involvement shows that the field is somehow corrupted and that there's something to be feared. So one of the leaks that came out in a Washington Post article quoted a particular technological development as evidence of the things that the NSA was doing, and it related to a kind of quantum control technique. And it turned out that very similar text appeared in the statement of work from one of my grants, which is just an open university-based research grant, because the kinds of challenges that the NSA is looking to overcome are very much academic challenges. These are scientific, fundamental science and engineering questions that they are asking academics like myself and my colleagues globally to try and overcome. It just says that a lot of the hyperventilation, a lot of the fear that's developed about what role agencies like the NSA or other military organizations have in funding this kind of research are really quite overblown. Feynman obviously has been an exceptionally influential person in our community broadly, quantum mechanics, just modern physics at large. But this idea of making a simulation of nature has turned into one of the most compelling near-term applications of quantum mechanical systems. As I said earlier, it's emerged that the idea of building a very, very large-scale quantum computer for, say, factoring may be very difficult, may be more difficult than initially anticipated. And very smart people have started thinking about what you could do with much, much smaller systems. So quantum simulation, the idea of making a quantum mechanical scale model of much more complicated systems, is an example of what Feynman was talking about, where you try to make a scale model that captures the behavior of something much larger and much more complicated. For instance, some process in chemistry or a process in material science that gives rise to phenomena that are very difficult to explain otherwise. And our community has grown excited about the prospect that with even medium scale, that is few hundreds or a few thousand quantum bits instead of billions or tens of billions or something else that may emerge in the context of factoring, we may be able to solve, or at least gain new insights into very challenging problems that sound esoteric at first, but really have huge implications, as we discussed before, for global security, for energy, and the like. There is interest globally in questions of how quantum mechanics and quantum technology can be applied to virtual reality and artificial intelligence and the like. I think these are interesting questions to ponder. I think that's very different than things we should be thinking seriously about or worrying about in the near term.